Hello, welcome to a video continuing on our subtopic of relativity, and we'll continue looking at time dilation, but also this time length contraction as well. So some subatomic particles exist in the laboratory for very short time periods before decaying. These same particles are detected as part of cosmic ray showers in the atmosphere, travelling at relativistic speeds close to the speed of light. Time dilation effects allow these particles to travel significant distances without decay. In Stage 2 physics, the expectation is that you're able to calculate time dilation factors for subatomic particles, that you're able to calculate and compare distances travelled by subatomic particles in stationary and moving reference frames, and that you're able to solve problems involving subatomic particles moving at relativistic speeds. So, subatomic particles. As you might guess, they're particles that are the constituent particles of atoms, in other words, the particles that make up atoms. Examples include electrons, protons, and neutrons, but there are some more obscure ones as well, for example, quarks, leptons, and bosons, and there's different subcategories of these. These particles have very short lifetimes, and they exist for less than a second before rapidly decaying. If these particles travel at high, so relative velocities, so velocities that are greater than 3/10 of the speed of light, and they're measured by stationary observers or observers in stationary reference frames, their time that they exist for can be extended, and this is a result of time dilation. This time dilation also allows particles to travel greater distances before decaying as well. Muons are a type of subatomic particle, and they're produced when cosmic rays collide in the Earth's upper atmosphere. I think I forgot to include a picture of them, but they're quite cool to look at. There is a picture of them in your workbook, so have a look at that, it's quite cool. So we have an example question here. Muons are subatomic particles that are produced when cosmic rays collide in the atmosphere, as I just said. A muon is created 15 kilometres above the surface of the Earth and moves at a speed of 0.992 of the speed of light, so 0.992 c. Its mean lifetime at rest is 2.20 times 10 to the negative 6 seconds, so 2.2 microseconds, and we have to predict the distance it will travel before decay. So to do this, we can just use our regular velocity equation. Velocity equals distance over time, and this is time in the moving reference frame, so t0. And of course we can just rearrange this, so this will be s equals velocity times time in the moving reference frame. This will be 0.992 and then times speed of light, which is 3.0 times 10 to the 8, and then for our t we'll be using 2.20 times 10 to the negative 6, so there's our 2.2 microseconds. This, when you pop it into a calculator, will end up being 654.72 meters. So even though when you read a question like this it does sound like we're dealing with something quite complicated, which we are, when we're solving these equations they can end up being quite simple, so you just have to know what information the question is providing you and how you need to use it. So the next thing that we have to find is the muon's lifetime as measured in the reference frame of a stationary observer. So this is where we use our time dilation equation. So that equation is T is equal to the Lorentz factor by time in the moving reference frame, and that is of course equal to 1 over the square root of 1 minus v squared, so the relative velocity between the two reference frames squared, over the speed of light squared, and then times time period in the moving reference frame. So in this situation here, I'm going to make this a bit bigger, hopefully. We'll be subbing in to this equation here. Now for the relative velocity, we can just use this value here because the stationary reference frame is obviously stationary, so the relative velocity is going to be whatever the velocity is in the moving reference frame, and that's 0.992 of the speed of light. So that will be 0.992 c squared, still all under the square root sign. I think I've just made the fraction line the square root sign, but you get the point. And then that will be speed of light squared, which is obviously 3.0 times 10 to the 8. And then of course that is all times by the time period in the moving reference frame. So there we go. Even though it does say here its mean lifetime at rest is 2.20 times 10 to the 6, it's at rest in the moving reference frame. So that could be occasionally a point of confusion, but it's more just knowing what reference frame information is specific to. Cool. I'm not going to bother writing out the 3.0 times 10 to the negative 8 here and here for the C's, because I presume we know what that is. And if you were to put this entire thing into your calculator, you would end up with 2.46 times 10 to the negative 5 seconds, or this is equal to 24.6 microseconds. So that's the lifetime as measured in the reference frame of a stationary observer. So 24.6 microseconds in the stationary observer's reference frame as compared with 2.2 microseconds in the moving reference frame. The last thing we have to find is the distance travelled as measured in the reference frame of the stationary observer. For this, we go back to our displacement equals velocity times time equation. Hopefully you can see that's a rearrangement of velocity equals displacement over time. And we just sub in our values for the stationary observer, or the stationary reference frame. So in this situation, velocity is still going to be this, but the time, which is dilated in the stationary reference frame, is going to be 24.6 microseconds, which is 2.46 times 10 to the negative 5 seconds. So we just sub that into here. That's going to be S equals 0.992 C by 2.46 times 10 to the negative 5. So in your calculator you'll put 0.992 times 3.0 times 10 to the 8 times 2.46 by 10 to the negative 5. Putting all of that into your calculator, you should end up with 7,320.96 metres. So that's how many metres, or that's the distance the muon travels before it decays according to a stationary observer, so an observer in a stationary reference frame, and that's compared with only 654 metres, 654.72 metres that the muon itself in its own reference frame travels. So if a muon was a sentient thing, maybe it is, I don't know. As in, I don't know if like they have feelings or whatever. Then it would only perceive itself as travelling 654 metres and 72 centimetres, whereas like a human standing and watching it from a stationary point would observe it travelling almost like 7.3 k's. So, like time, in special relativity, length is also not absolute, and it's impacted by an object's motion in an inertial frame of reference. So it's a bit weird to think about these things given we perceive like tangible physics, but theoretically in special relativity, time and length are as, I guess, malleable or changeable as something like velocity or acceleration. So they're not absolute and they can be altered depending on the reference frame that you're in. So, like time dilates in a moving reference frame according to an observer from a stationary reference frame looking into the moving reference frame, length contracts. So an object moving at relativistic speeds appears shorter to an observer in a stationary reference frame, and the length is given by length in the stationary reference frame is equal to length in the moving reference frame divided by the Lorentz factor. In stage 2 physics, you'll need to be able to solve problems using this equation, and you'll also need to be able to explain the effects of length contraction on objects moving at relativistic speeds. As I kind of just touched on, special relativity theory states that the length of an object moving at a relativistic speed, so something greater than 3/10 the speed of light, as I mentioned before, the length appears to be contracted, so it's shorter, as observed from a stationary reference frame, and this length contracts in the direction parallel to motion. So we can see with our tennis ball up here, this tennis ball would be travelling at different speeds, and as it's getting, as there's like less and less width to it, it would be travelling at a higher fraction of the speed of light. And you can see that it's only contracting horizontally. It's still got the same vertical length, so it must be moving horizontally, and so it's only contracting parallel to that horizontal motion. The length of an object as measured in a stationary observer's reference frame can be calculated using the equation that I mentioned before, and that is equal to this with the Lorentz factor that's been subbed in. So if you were to sub in 1 over the square root of 1 minus the relative velocity between the reference frames squared divided by the speed of light squared into here, then you'd end up with the length in the moving reference frame times by the square root of 1 minus relative velocity squared over the speed of light squared. So just as the Lorentz factor is equal to the time period in the stationary frame of reference over the moving frame of reference, it's also equal to the length in the moving frame of reference divided by the length in the stationary frame of reference. And this is of course equal to 1 divided by the square root of 1 minus b squared over c squared. The minimum value for the Lorentz factor is 1, and this occurs when the relative velocity here is 0. So hopefully you can see that if this b squared here was to be equal to 0, then this whole equation here would be equal to 1. As v squared increases, the denominator becomes smaller in this fraction, and therefore if you're dividing by a number smaller than the numerator, then the overall number that fraction equals out to is going to get bigger and bigger. So as the relative velocity approaches the speed of light, the Lorentz factor increases. If we look at these equations here, the minimum Lorentz factor value, which is 1, is going to occur when time in both reference frames is equal and when the length in both reference frames is equal. Hopefully you can see that given that all of these equations equal each other, these lengths and times are going to be equal when the relative velocity between the reference frames is 0. Both the table here and the graph here indicate or illustrate that the Lorentz factor sharply increases as the ratio of relative velocity to the speed of light increases. The bottom graph on the left, so this one here, illustrates that as relative velocity increases, time dilates in the stationary observer's reference frame. So the ratio of time in a stationary observer's frame to the time in a moving object's reference frame increases. So what that is essentially saying is as we increase along the x-axis, this line here increases, so the corresponding y value over here, which is the ratio of time in the stationary reference frame to time in the moving reference frame, so t and then t0. The bottom right graph illustrates that as relative velocity increases, so as we go along the x-axis, length contracts in the stationary observer's reference frame, so the ratio of length in the stationary observer's frame to length in the moving object's reference frame, so L0, decreases. So as we go further along the x-axis, the y value decreases. So as an example, a stationary observer on Earth sees a car travelling at 2.5 times 10 to the 8 metres per second. When stationary, the car is 3 metres long. Calculate the length as seen by a stationary observer. So this speed here is a relativistic speed. It's at least 3/10 of the speed of light. In fact, it's much more, about 5/6. And we need to calculate the length that a stationary observer sees. So our length in the moving reference frame is 3.0 metres, because when the car is stationary, its reference or its relative velocity is 0. So that means that the length in the moving reference frame is going to be equal to the length or the length observed in the moving reference frame is going to be equal to the length observed in the stationary reference frame. But we need to work out what the length is going to be when it's travelling at this speed here. The velocity of the vehicle is going to be 2.5 times 10 to the 8 metres per second, because our relative velocity is going to be equal to our velocity here, because the stationary observer has not got any velocity at all, so whatever the velocity of the car is going to be the relative velocity. So we have these values here. We can use this equation here, so L equals, or length in the stationary reference frame equals length in the moving reference frame divided by the Lorentz factor, and that of course will be equal to length in the moving reference frame times by a square root of 1 minus relative velocity divided by the speed of light. So this will become 3.0 metres, so subbing into this value here, times by square root of 1 minus and then v here, so 2.5 times 10 to the 8 squared over c, 3.0 times 10 to the 8 squared, just in the square root symbol. This, if you plug it all into a calculator, is going to end up being about 1.66 metres. So you can see that the length in the stationary reference frame is shorter than the length in the moving reference frame. So the length has contracted. The key to these problems is working out if the length or time that you've been given corresponds to the moving reference frame or the stationary reference frame, and how you can use pieces of information to determine other pieces of information or when they match up. So for example, with this one here, even though it says when the car is stationary, so you might think that it's for the stationary reference frame. This is actually talking about the velocity of the vehicle being 0 metres per second in its own reference frame, and in its own reference frame the length is always going to be 3 metres, so this car is always, if it could think, it would always perceive itself as being 3 metres long. So when the vehicle is stationary, the stationary observer can observe that it's 3 metres long, but for the car in its own moving reference frame, it's always going to be 3 metres long, but to the stationary observer, the length decreases as the car travels faster and faster towards the speed of light.